Hello. In this and the next few lectures, I will be discussing what is known as alternating current. Some time back we had talked about direct current circuits, and I would like to point out that in our day-to-day use, it is the alternating current which is more prevalent than direct currents, and we will be discussing the various properties that go with it. But before we do that, let me remind you of what you have done earlier on Faraday's law. In our discussion of Faraday's law of electromagnetic induction, we had seen that if we have a situation where the magnetic flux changes with time, then an EMF is produced. The EMF relationship is given by the mathematical statement of Faraday's law, which says EMF is equal to minus n d phi by dt, where phi is the flux through each turn and n is the number of turns. If you recall, our definition of flux was integral of B dot ds over a surface. The formula is written usually with a minus sign, and that is because this is a reminder of what is known as Lorenzs law. The Lorenzs law talks about the direction of current induced in the circuit. So according to Lorenzs law, now the direction of such induced current is always such that the magnetic field that such a current produces opposes the change that produced it. In other words, it tends to negate whatever change was being sought by the agency producing this current. Let's push this idea a little further. Supposing we have a rotating coil in a uniform magnetic field. So I will just give you a schematic diagram. So I have a coil which is rotating in a constant magnetic field. So this is the rotating coil. And let's suppose this is the direction of the magnetic field, which is uniform. And the coil, of course, moves around this axle. And suppose the direction of B makes an angle theta with the perpendicular to the plane of the coil. So let me represent it like this. So supposing this is the direction of the magnetic field, and this is a section view. So this angle is theta. So this is the way it's rotating. So therefore what happens is this, that the flux produced is, remember this is B dot A, that is B dot ds. So it is B times A times cosine of theta, which is of course a function of t, and that's equal to BA cos omega t, because the coil is rotating with a uniform angular speed omega. So therefore the EMF generated by it, according to Faraday's law, is N d phi by dt, which is equal to NBA omega sin omega, where N is the number of turns in that coil. Now this I can write as E0 sin omega. So since you notice that this EMF is changing sinusoidally, so therefore this will produce a potential difference which also changes sinusoidally. So let me say that the potential, the voltage V, is given by an expression like Vm sin omega t. Now suppose I am to plot this voltage against time. So this is a representative diagram in the sense that when I say t equal to 0, it doesn't mean that is the instant when the voltage was switched on, but any particular time you can take it as time t equal to 0 and proceed for one cycle. So supposing at my time t equal to 0, this is axis is time, my voltage happens to be 0, and then I go through one cycle. So this magnitude, the maximum magnitude of it, so this is my voltage V as a function of time, and this is Vm, that's the maximum voltage. So in this picture, what I have done is to say V equal to 0 at time t equal to 0. Now the voltage returns to the same value. So this is time t equal to 0 after a time capital T, passing through a full cycle, and this t, after which the voltage at any point in the circuit returns to the value that it had time capital T before, is known as the period. So t by 4 after the initial time, the voltage becomes maximum, and this is t by 2, this point where it becomes maximum but in the negative direction is 3t by 4, and this is full cycle t. Now if you want to compare this graph with that of what happens in a DC circuit, the DC means there is no time variation. So this is the DC voltage. So this definition is V of time t plus t is equal to V of t. Now this omega is related to the linear frequency. Remember the linear frequency f is equal to 1 over t, and omega then is 2 pi times f, which is equal to 2 pi over t. Now let me then write down the simplest possible AC circuit. So the symbol for an AC, remember in DC circuit I had a battery type of symbol, but here this is given like this, and this is V equal to Vm sin omega t, and all that I have is a resistance in the circuit. So I'm looking at what happens when a alternating voltage is applied in a circuit which consists of a resistance only. So let me assume Ohm's law. So my current I then is given by this quantity Vm divided by R times sin omega t, which we will write as Im maximum times sin omega t, where Im is the maximum value of the current in the circuit. Now, I had already shown you the way the voltage varies with time. You notice that the variation of the voltage, just for comparison's sake, was given by Vm sin omega t. So what you realize is that the time variation is identical there. The current's maximum is Vm divided by R. So therefore, the magnitude of the maximum current would depend upon what the resistance R is. So if I am in the same diagram plotting the difference, plotting both the current and the voltage in the same diagram, let's do that. So I have a time diagram, x-axis is time, and on y-axis I will plot both the voltage and the current, obviously because their scales are different, their units are different. So I will have two different scales on that. So let me first plot the voltage, for instance. So this is one cycle, but let me just write down another cycle also, half cycle. So this is your Vm. Supposing in the same diagram, so this is Vm. Supposing in the same diagram, I also plotted the current. In other words, the current will be plotted, but with the scale being different. So voltage is in volts, and I will be plotting here the current will be in amperes. And depending upon the value of R, I'll get a different value of I maximum. But the important point to note is, when the voltage becomes maximum, the current becomes maximum, and vice versa. So therefore, my plot of the current would be something like this. Each part is identical. This doesn't look identical because of freehand drawing. So this is your Im. So the point that I am trying to make is this: time here, or let's say omega t, doesn't matter. Point that I am trying to make is the current I becomes maximum or minimum at the same time as the voltage does. Now, one of the things which is frequently done is to plot what is known as a phasor diagram. Now, a phasor diagram is basically a polar curve with its x-axis being a reference line at time t equal to 0. So let me just plot this and I will go on explaining what is a phasor diagram. So this is some reference line I have taken with respect to this time, that's what I call as the initial time. I am plotting everything. So I assume that at time t equal to 0, I have a vector of length Vm, which is aligned with this axis. So let me put it like this. Imagine one end of that vector is at the point O origin, and it has a length equal to Vm, and end point is A. So let me say that OA vector has a magnitude equal to Vm. Now, what I assume is this, that keeping the end O fixed, this vector rotates about an axis which is perpendicular to the plane of the paper, passing through O, with an angular velocity omega. So that at time t equal to t, the angle that it has swept is omega t, and this vector then lines up like this. So the magnitude still remains Vm, but it goes to the point B, where this point, this angle is omega times t. Now, suppose I take my variation of voltage with time, as I have said a little while back, V of t is equal to Vm sine omega t. This tells me that if you take the projection of this vector VOB at time t equal to t, then this gives you the instantaneous value of the voltage. Now, supposing instead I had taken Vt equal to Vm cos omega t, then the projection along the x-axis would have given me that. Now, let's look at what happens to the current. Now, in a phasor diagram like this, I plot both the current and the voltage in the same diagram, but since current and voltage have different units of measurement, I can choose my scale appropriately to make these lengths of vector the way I want it. So what we do is this, that suppose I write I of t for a purely resistive circuit to be given by Im sine omega t. Remember, the current and the voltages are in phase. Then at all time the current phasor is lined up along the direction in which the voltage phasor is lined up, and suppose I decide on a scale in which the current magnitude is given by the length of the vector OC. So OC magnitude is Im. Then the projection of this OC at time t equal to t gives me the instantaneous value of the current. Now, an important point to take home from this is, for a purely resistive circuit, the current is in phase with the voltage. Now, let us look at what is the average value of such a current. But before I do that, let me define what is meant by the average of a quantity over a cycle. So, supposing I have a time dependent quantity f of t, the average of f of t over a period it is written like this, or you could also write it like f bar of t, whatever, there is no standard way of doing it, is 1 over t integral from 0 to t of ft dt. So let us look at a time dependent quantity such as current, which is given by I of t equal to Im sine of omega. So average of I of t, if you look at this definition, would be Im 1 over t integral from 0 to t sine omega t dt. You recall that integral of sine omega t is minus cos omega t by omega. So it is Im 1 over omega t, and if you take the limit, it is cosine of 0, that is 1, minus cosine of omega times capital T. So I have to find out what is this. Recall by definition of time period, I have omega times capital T is equal to 2 pi. So therefore, what I have here is cosine of 2 pi, and but cosine of 2 pi has the same value as cosine of 0. So therefore, this quantity is equal to 0. And this would also be true for functions such as, also valid for you could have sine 2 omega t, 3 omega t, etc. Or even cosine omega t, cosine 2 omega t, etc. There is another relationship that we would require as we go along. How much is average of sine square omega t? So let us plug this into the definition. So average of sine square omega t is 1 over t integral sine square omega t dt from 0 to t again. You recall your multiple angle formula, which tells me that sine square omega t is written as 1 minus cosine of 2 omega t divided by 2. And I have just now told you that any multiple of sine or cosine omega t integrates out to, averages out to 0. So therefore, the only thing that I am left with is this factor half dt, which gives me t. So therefore, this gives me 1 over 2, and that is because average cosine of 2 omega t equal to 0. We will be using this as we go along. So what we have shown in the process is the average current is 0. Incidentally, this doesn't imply that the power dissipated is 0, because power is given by I square R. So average power dissipated in the circuit is average of I square R, and which is equal to Im square R average of sine square omega t, which I just now proved the average of sine square omega t is half over a cycle. So it is Im square R divided by 2. So you notice that this formula has some similarity with the power dissipated in DC circuits, but for this factor of 2. Now we could remedy this situation and make the two formula very similar, provided we define a new quantity which is known as the root mean square current. Usually denoted by IRMS. I can similarly define root mean square voltage, but let's stick with this now. As the name suggests, the root mean square is take the square, take the mean of the square of the thing, and then take a square root of it. So the way one defines it is like this. It is square root of average of I square t. But we have just now seen that I square of t is Im square by 2. So therefore, IRMS happens to be Im divided by square root of 2. And likewise, we can define a VRMS equal to Vm divided by square root of 2. Now, if you are plotting, for example, the current I of t, remember that my current has a sinusoidal variation. So this was my maximum, I max. The root mean square, which is Im by square root of 2, is about 70% of this value, because 1 over square root of 2 is about 0.707. So therefore, my root mean square value is somewhere here, 1 by root 2 Im. Now once you start using root mean square current instead of the maximum current in this circuit, you realize immediately that I can write P average as equal to I RMS square, that is because there is a 1 over square root there, 2 there, which will take care of the factor of 2 times R. And the formula would then be looking very similar to what we had seen in case of a DC circuit. Now, I would like to point out that when we talk about the voltage supplied to our homes, for instance, in India, for instance, the supplied voltage is AC and varies generally, it is supposed to be 240 volts, but it generally varies between 220 to 240. Is between 220 to 240, supposed to remain around 240, and the frequency, linear frequency, nu, is taken to be 50 Hz. Since many of our textbooks are of American origin, I would like to point out that in the USA, the household supply is about 120 volts and the frequency is 60 Hz. And that is the reason why when you go abroad to a different country, you need adapters to match if your equipments are designed for a particular voltage or a frequency, then you need adaptations. So we have discussed already what happens when an AC source is connected to a resistor, but that's not really a very interesting situation. The alternating voltage, they become more interesting when you put into the circuit other elements, in particular the inductance and the capacitance, about which you have learned in your previous lectures. So let me first talk about an alternating source applied to or connected to a purely inductive load. What it means is that the circuit does not have any resistance, no resistance, and the only thing that is there in that circuit other than your AC source, which will take it to be Vm sin omega t, is an inductance. Now once again, I'll use the Kirchhoff's law here. And you remember from your discussion of Faraday's law and the properties of inductances that inductance provides what is known as a back EMF. So what we get is this, and this back EMF provided by the inductance is minus L di by dt. So therefore, if I use the Kirchhoff's law in the circuit, I get V of t at any instant of time minus L di by dt is equal to 0. Which tells me that di by dt is Vt over L, but Vt is known to be Vm sin omega t, so this is Vm over L times sin omega t. If I integrate this now, so my I as a function of time will be Vm over L sin omega t, which is equal to minus Vm over L omega cosine of omega. Now here I have taken the constant of integration to be 0 because we have seen that the voltage has no constant component and it is symmetrically oscillating around 0. So therefore, my current should also not have any constant component and should also oscillate symmetrically about 0. So notice this, in case of a purely resistive circuit, the trigonometric form of the time variation of both the current and the voltage was identical, but now I have a difference. And since I can write this cosine function as sine of omega t minus pi by 2, that takes care of the minus sign as well. So what I am getting in this process is that the amplitude, current amplitude, is given by Vm over L omega. So this is current amplitude. Another interesting thing you notice is this, that since the voltage is varying as sine omega t, but the current in this circuit is varying as sine omega t minus pi by 2. So what I notice is this, that the current falls behind the voltage, or in our language, there is a phase lag of pi by 2 with respect to voltage. The purely resistive circuit had no such lag, but now we have realized that the current lags behind the voltage. This quantity, which comes here as in the expression for current, is given a name, this omega times L. Now, if you compare this with the direct current circuit, you realize that this is playing the role of resistance, but there is a difference. This quantity depends on omega, and this is given a name, it's called inductive reactance. usually denoted by XL. So XL is equal to omega times L. So basically what is happening is something like this. The XL, supposing I am plotting this versus the frequency, then XL is linear. This is your XL variation. But as the frequency increases, the current decreases. So this is the way your current would, or let's say current at any instant of time would change, provided I am plotting it against the frequency. So this is called inductive reactance. So what actually happens is this, that as the frequency increases, the inductance value of the reactance increases, and as a result the current decreases. Let me plot the current and voltage as a function of time. So let me draw the voltage waveform. So this is completely one cycle, but let me also draw a little more than that. So this is my time t, and what I have plotted here is the voltage in this blue. So this is V of t, this is t by 2, this is t, this is of course 3t by 2. Now in the same plot, first let me write down what I have plotted here is voltage, of course in volts. In the same figure I'll be plotting the current, but since current and voltages are measured in different units, I can choose different scales for this. And I've seen that for an inductor the current lags the voltage in phase by pi by 2. It means it lags by quarter of a cycle. So let me make a note here that for the inductive circuit, current lags the voltage in phase by pi by 2, which means by 1/4 of a cycle. So in this figure, when the voltage is 0, my current would be negative and maximum magnitude. So let me plot it here, and this is quarter of a cycle. So therefore that when the voltage has reached maximum, my current would become 0. So the it's nice to divide this by t by 4. So my current would be something like this. Well, the doesn't exactly look like a sine curve, but since it's a freehand drawing, it is sort of an acceptable thing. So what I've got here is this. This is the red curve is I of t, and you can see that it is lagging in phase by t by 4, so that it is maximum negative at time t equal to 0 when voltage is 0, and when the voltage has reached its maximum, the current is 0, and then as the voltage remains positive and is decreasing and has just about reached 0, the current has reached its maximum, and this maximum is my IM value. So let me write down, in red I have current in amperes, of course, and this magnitude is what we wrote as VM. So let's look at How does the phasor diagram look? This is for an inductive circuit. So let me, for reference, reproduce the current and the voltage curve. Remember, this was my voltage. So this is my time t, and this is time t by 4, t by 2, 3t by 4, and of course time t equal to 0. I repeat that this doesn't mean that I am switching on the EMF at time t equal to 0, but it is a representative curve starting from any origin that you have taken for the time and with respect to which I am drawing this curve. Now, the corresponding current curve was something like this. Remember that this is the way the current behaves. So this is current and this is voltage. So if you look at this diagram and find out what is the phasor diagram looks like for this. So as before, I take the initial line to be t equal to 0, which is the reference line. The voltage, which has a magnitude Vm, is a vector of length OB. So once again, OB magnitude is equal to Vm, and at time t it makes an angle omega times t with the x-axis. As I have said several times, the projection along the y-axis gives me the instantaneous value of the voltage. Now, since the current lags behind the voltage by pi by 2, it means that the current becomes maximum a full quarter of a cycle after the voltage does. Now, the thing is this, that because the lag, the time lag between the voltage and the current is pi by 2, so when this is in the first quadrant, the corresponding current will be in the fourth quadrant, and this angle will be 90 degrees. So this is my current there. This is what I had represented by OC there. So OC is magnitude is IM. And of course, it automatically means that if the voltage goes to the second quadrant, imagine this entire thing being rigidly being rotated by certain angle, taking OB to the second quadrant. By that time, the current would then come to the first quadrant. So current would also become positive. So this is the way it is. When voltage is positive, the current is negative in the first quarter cycle. In the next quarter cycle, both of them happen to be positive. In the third, I have a negative from here and a positive from there. And finally, to conclude it, both negative. Voltage as well as current are both negative. What about the power in an inductive circuit? So let's look at instantaneous power. So power is given by I times V. This is instantaneous power. So instantaneous current multiplied by instantaneous voltage. And this is equal to Im sine omega t minus pi by 2, and V is equal to Vm sine omega t. So it's equal to Im Vm. We had seen that this is minus cos omega t, and this is of course sin omega t, which is nothing but minus Im Vm by 2 sin 2 omega t, which tells me that the power over a cycle is 0. The situation is very similar to what happens in a mass spring system. Supposing I have a mass on a frictionless table connected by a spring, no friction. Now, as you set the system into motion, the mass gains kinetic energy at the expense of the potential energy of the spring, and later on returns that amount of energy as the potential energy of the spring, and it loses its kinetic energy. And it's a conservative system, because the only other thing here which could take away or dissipate power, that is the friction, which we have assumed that doesn't exist here. And an identical thing happens in case of your inductors in the circuit. So inductor in one cycle, part of a cycle, would absorb power from the circuit, actually retain it, and return it to the circuit in the next quarter cycle. The effect of what I said is that for an inductive circuit, the power over a cycle is 0. So for an inductive circuit, the average power equal to 0 over a cycle, which is another way of saying that the purely inductive circuit conserves energy. And compare this, a purely resistive circuit, for which the average power was shown to be equal to I square R, well actually I RMS square R. So let me elaborate on this a little bit. Let us plot the current voltage relationship in this case. So this is x-axis is time, and in the same plot I'll be plotting both the voltage and the current, and this blue line on the blue curve is my voltage Vt, which is obviously in volts. So Vt in volts. I will also plot now the current in the same curve in amperes. So AIT in amperes. And since I know that the current for an inductive circuit lags behind the voltage by quarter of a cycle, the curve that I get for the current is something like this. Notice my scales are different, because in one case I am plotting current, in the other case I am plotting voltage. So this is I of t. Now let's consider an instant of time when the voltage is 0. Now since the current at that instant has a maximum, so therefore this is my time t by 4. And let me also give some labels to these. So this is Vmax, and in the red curve. Okay, this would be slightly different scale I have taken. So this would be I max. So let us look at how does current and voltage vary. In this cycle from T by 4 to T by 2, which is here, you notice my current is greater than 0. Not only that is increasing, that is di by dt is greater than 0, which implies that my voltage V of t is also greater than 0, which can also be seen, of course, in the voltage curve itself. So it tells me that power, which is I times V, is greater than 0 in this cycle. So since the power is greater than 0, it implies that the energy is absorbed from the source. So my various signatures are the following: voltage plus, current plus. Now let's go to the next quarter cycle. From T by 2 to 3T by 4. The current which had become maximum starts decreasing, but it still remains positive. So I is greater than 0, but di by dt is less than 0, which, as you can see from the curve and from the signature of di by dt, V of t becomes negative. So which means power P, IV, is less than 0, which means the energy that was absorbed in the previous quarter cycle returned to the source. In the next section, so this was my 3T by 4. So in this section, as we have seen, my voltage is negative, current is positive. In the next quarter cycle, from 3T by 4 to T, my current is less than 0 now. So is di by dt, which means Vt is also less than 0. But since both are negative, my power is greater than 0, which implies again that the energy is absorbed from the source. So this was from 3T by 4 to T. So here you notice this is negative and so is the current. Now if I went from T to 5T by 4, the situation would be simply a replica of what happens from 0 to T by 4, and there you can see that the current is negative, the voltage is positive. Once again it means that whatever energy was absorbed in the previous quarter cycle is returned back. So this is positive and this is negative. Let me close this discussion with a couple of examples. Suppose I have a 48 millihenry inductor connected to, some of these numbers I have chosen such that arithmetic becomes easy, connected to 240 volts 50 hertz supply. I need to find out what is RMS current. I don't have to tell you that whenever we are giving the value of voltage or current, they are RMS values. Otherwise, we would specifically point out that these are peak values. So in this case, my first job is to find out what is my reactance. My reactance is omega times L. Omega is 2 pi nu and nu is 50 Hertz, so 2 pi into 50. The inductance is 48 millihenry, so therefore 48 into 10 to the power minus 3. And that is 4.8 pi, which if you calculate works out to 15.08 ohms. So my RMS value of current is 240 divided by 15.08, just let's take it as 15, that's equal to 16 amperes. This value of current which we have obtained is much higher than the typical household current, which is generally limited to about 8 to 10 amperes. But that's primarily because in this artificial circuit that I have considered, I have not taken any resistance. Normally, resistances are there in the circuit which would limit the value of the current. So what we have done today is to define an alternating source voltage and seen that when this is connected to a purely resistive circuit, the current and the voltages are in phase. But when you connect it to an inductive circuit, then you find that the current lags behind the voltage. The second point is that in a purely resistive circuit, there is a power dissipation, which is given by the same formula as for DC, excepting that I have to change my definition of current to the RMS current, I square R. Whereas a purely inductive circuit does not dissipate power. Whatever power it absorbs in a part of the cycle is removed, returned back to the circuit in another part.